Okay, good afternoon, everyone. Thank you for taking the time to make it out to today's online seminar. My name is Daryl, and I'm with Midas. And before I begin, I just want to take a quick sound check. So if you can hear me, please use your GoToMeeting icon to raise your hand, just to let me know that you can hear me. Okay, perfect. So I can see that a majority of the hands are raised. For those of you who can't hear me or who can't hear me very well, feel free to just type into the chat box, and we'll see what we can do to alter our audio. Okay, so today's session will be the numerical modeling and training for seismic design. But before we get into that, I just want to give a brief introduction to the Midas e-learning courses. I see that we have a lot of first-time attendees here, so I just want to briefly review what these e-learning courses are about and how they can benefit you all. Okay, so what are Midas e-learning courses? Basically, they're a series of online technical seminars that we'll be hosting on various bridge topics, and each of them, or each topic, consists of 3 very specific and distinct parts that are all interrelated. So what is the why exactly are we hosting these courses? First and foremost, we wish to contribute to our clients as part of our technical services. So we find that a lot of our clients have requests or want to learn about certain topics. So we find that these seminars would be a good platform to share the knowledge and to share the skills that would be necessary to approach these challenging topics and to improve your professional skills as well as your professional knowledge. Also spreading technology. A lot of attendees here are users of our software, so we find this would be another great opportunity just to share the advantages of our software and to offer opportunities to learn how to use it as well as to try it out for yourself. And last but not least, we bring happiness to engineers and to lead to breakthroughs. So we find that through these courses, a lot of engineers are able to learn certain skills or design practices that are helpful to them and that will help them to work more productively and efficiently as well. Okay, so first, the first sort of session in each series is the technical seminar. So for each technical seminar, we'll actually have a guest speaker. So for example, a guest speaker from a design firm that uses our software, a local DOT or a university. He or she will give a detailed discussion, just introducing the topic, discussing certain specific bridge type as well as design considerations. They'll also discuss challenges that were faced and how specifically they're able to overcome them. So the main benefits of attending the technical seminar are first and foremost knowledge sharing. So all of our guest speakers are experts in their respective topics, so you can rest assured that you'll be receiving instruction from someone who has a very wide array of knowledge in this particular topic. Also, it's a great way to become introduced to a certain bridge type or a certain design consideration. So for those of you who are interested in learning about how to do other types of bridges or who are planning maybe to approach some more complex or high-end design work, this is a good opportunity to learn about how to get started with that as well as the challenges that you'll be facing. And also you learn about significant projects in North America by leading bridge design companies. So many of our speakers, they'll speak about projects that they worked on themselves. And a lot of these projects are landmark projects, or they're projects that are well known and that are a good source or sort of a good model to build upon. And last but not least, networking. So all of our speakers are open to questions and discussions. So these seminars are a great way to expand your professional network and to become acquainted with other engineers from around the country. Okay, so as you can see, we have a wide array of engineers or a wide array of guest speakers from different backgrounds, ranging from professors from universities, engineers from DOTs, as well as engineers from leading design firms. Okay, so after the technical seminar, the follow-up seminar will be the in-depth case study and discussion. So the main contents of this seminar will be, for example, related case studies in the U.S. and Canada. So in addition to the previous examples that you may have seen in the previous technical seminar, you'll also get to see sort of a wider array of projects that relate to the same topic that was discussed. And also you'll be introduced to the latest technologies for numerical modeling and bridge engineering. So the main benefits of the in-depth case study and discussion seminar is first and foremost you'll be able to learn about the advantages of finite element analysis in bridge engineering. So for those of you who are getting started with finite element analysis or who would like to pursue finite element analysis in the future, this is a great way to become introduced to it, to learn about the specific benefits of finite element analysis and how specifically it could apply to your own projects. Also, you'll be able to explore different approaches for modeling, analysis, and the design of bridges. So once again, this is a great opportunity to expand your professional knowledge and to see what other design approaches are currently being used in the industry. And then also you'll be able to use the latest technology in your everyday design work. So I'll be talking a little bit more about this later, but everyone who attends our seminars, if you're not currently using Midas Civil, you'll have the opportunity to receive a free trial version of the program so that you can try it out for yourself and that you can try maybe modeling one of your own projects on it, or you can try modeling one of the projects that we discussed just to see how you like using the software for yourself and to see how finite element analysis provides specific advantages. Okay. And then our third, or the third and the concluding course of this series will always be the numerical modeling and analysis training, which is the session that you're all attending today. So during this session, we'll have a step-by-step modeling of the bridge project. So in the first two sessions, you were introduced to general topics, you're introduced to a specific topic, but you were introduced to general sort of principles of that topic. But during the numerical modeling and analysis training, one of our bridge engineers will give you a step-by-step sort of tutorial or demonstration of how to use what you learned in the previous two sessions and how to apply it specifically into a project of your own. So you learn about different modeling techniques, output extraction, and also design checks for various codes. And the main benefits are, you get to learn about numerical modeling. So something that's becoming more prevalent in the engineering world now is the use of numerical modeling software. So for those of you who are trying to maybe get caught up on it or who are first being introduced to numerical modeling, this is a great opportunity to continue to learn. You can master, or you can sort of become a master of modeling different types of bridges. So once again, for those of you who are looking to model different bridge types or who are looking to pursue different types of projects, this is a great way to become introduced to different bridges and how to model them and how to design them. You can explore concepts of different analysis types, get the latest updates of North American design codes, and then once again, all attendees will receive free training software. For those of you who currently don't use any type of numerical modeling software who'd like to try out Midas Civil, we'll be in contact with you and we'll get you started with your trial version shortly. Okay. And last, I just want to show you just a quick screenshot of Midas Civil. So as you can see, this is just what our bridge software looks like. It's very advanced. It's very easy to use and easy to learn. And we do provide custom training for those of you who maybe want to see it for a specific type of a topic that we haven't previously discussed on the software. We can provide that for you. And once again, Midas Civil provides excellent features that will help you to design and analyze your bridge projects with greater efficiency, greater productivity, and it'll help you to also expand your market so you can be able to approach all different types of bridges as opposed to the ones you've been currently doing. But anyway, we'll get more into that later. So now I'd just like to turn the time over to Nithil Malguri, our senior bridge engineer, and he'll be giving you the demonstration for seismic analysis.
Thank you, Daryl. Hello everyone, I'm Nithil from Midas, and today I would be giving you a session in which I'm going to talk about the detailed pushover and response spectrum analysis in Midas Civil. Before I actually start, I would like to make sure that you guys can hear me properly. So if you can hear me properly, please either raise your hands or you can use the questions window in your GoToMeeting control panel to reply with a yes. Thanks a lot for your feedback. So I can see that almost everyone can hear me properly. If you guys have any issues with the audio, please let us know through the questions window and we will try to resolve your issues from here. So today we'll be talking about demand and capacity evaluation. As you know that when you perform seismic evaluation as per AASHTO LRFD Seismic Design code, you have to perform step-by-step specifications as defined in the code, and we had two sessions that we did earlier. The first session was done by Ling Zhao from Michael Baker, in which he talked about the practical approach to displacement based design, and in the second session I talked about the different code specifications which talk about the seismic design criteria. So before I actually start the training on pushover and response spectrum analysis in Midas Civil, I would like to do a brief recapitulation of what was discussed in session 1 and 2. And I hope everyone can see my screen. Okay, so first of all, let me talk about the force-based design. This discussion was done by Ling Zhao from Michael Baker, in which he talked about how the force-based design was used for seismic evaluation of the bridges. Here you can see the difference between the elastic analysis and the inelastic response. And what we used to do is we used to obtain an equivalent force which is obtained by earthquake. So whenever you apply an earthquake load to the bridge, you will obtain a certain force on different elements, and basically you design the elements based on that load so that in a way the bridge remains safe for a specific type of earthquake. But the most recent approach for the seismic design is moving from force-based design to displacement-based design, and this again was discussed in depth by Ling Zhao. And here you can see that in displacement-based design, we take care of the inelastic response of the bridge, and basically we calculate the demand which the bridge might need in the event of an earthquake and what is the capacity of the bridge. And the demand must be less than the capacity, and this is the whole principle behind the displacement-based design. Ling Zhao also compared between the force-based design and the displacement-based design, and he quoted out certain specific points of distinction between the force-based and the displacement-based design, and I have listed them out for you. So as you can see on your screen now, these are the distinctions between the force-based and the displacement-based design, and the ones in red are the most significant. So you can see that in the force-based design, we determine the elastic demand forces by dividing the forces by a response modification vector. And in the displacement-based design, we do the displacement demand check against a displacement capacity. And the most important of them all is that for the force-based design, we do the capacity protection is assumed, and for the displacement-based design, the capacity protection is assured. So basically, it's a better way of doing the seismic design check. And the capacity protection is done for column shear capacity, pier cap, foundation, and joint. In the second session that was done by me, I talked about the various steps which are involved in the AASHTO LRFD Seismic Design criteria to perform the displacement-based design, and I have given you the flow chart in which there are certain steps that you need to follow to perform this kind of a check. And here we talked about a bridge which was a conventional bridge, and we performed elastic dynamic analysis with the provisions from AASHTO LRFD code, and we obtained the demand in the event of an earthquake. Similarly, we obtained the demand in the y direction, and then we performed the pushover analysis to obtain the capacity in the x and the y direction. And then the capacity check was done, and this way we did the discussion on this kind of a bridge by following the procedure as given in the AASHTO LRFD Seismic Design criteria. Now I would like to talk more in detail about the seismic analysis, what are the different type of seismic analysis that you can perform, and what are the different advantages and disadvantages of these type of analysis. So before we actually start learning how to perform the seismic analysis in Midas Civil, I will take you through a brief introduction or theoretical background of these different type of analysis, and then we are going to simulate those type of analysis in Midas Civil. So first of all, let me talk about what seismic analysis is. So seismic analysis is a subset of structural analysis, and it is the calculation of the response of a bridge or building structure to earthquake. So basically, in the event of an earthquake, we determine what will be the effect on the structure, and to obtain that effect, whether it is in the form of force or displacement or deformation or whatnot, it is known as seismic analysis. And why is it important? It is important because, you know, in the event of an earthquake, if the earthquake occurs, we do not want our structure to fail, or we do not want our structure to collapse, because it might, you know, lead to loss of property or loss of lives. So that's why we want our structures to be safe, and that is why the seismic analysis is becoming the need of the hour. So let us talk about the consequences of earthquake. What actually happens when an earthquake occurs, or in the event of an earthquake, what are the different consequences that are faced by a building or a bridge. So first of all, the earthquake applies lateral force to the structure. It can apply lateral force in any direction, and the force is in the form of an acceleration. So basically, whatever force you apply to a structure or any other object, it will become, as you know, that force is equal to mass multiplied by acceleration. It's a sudden force, and it causes the vibration inside the structure. And it might happen that due to the lateral movement of the bridge or the building, it leads to secondary effects on the structure, which we call as P delta effects. And since the structure deforms beyond a limit, the steel and the concrete which is inside the structure, which is responsible for the structural integrity of the bridge or building, they might attain a nonlinear behavior as shown here. So these are the consequences which a bridge or a building might have in the event of an earthquake. And as you can see here, these are some of the bridges that I've shown here and some of the catastrophic failures of the bridges in the event of an earthquake. You can see how the bridges have collapsed during an earthquake. So first of all, let us talk about the different type of methods that we utilize for performing the seismic analysis. So here I have divided the different structure action and the type of analysis we perform for seismic analysis. Here you can see that I have distinguished the structure behavior, which can be either elastic or nonlinear, and the type of analysis that we have performed, which can be either static or dynamic. So if the structure is supposed to behave elastically and we perform static analysis, we call this approach as equivalent force approach. So what we do in this method is we apply an equivalent lateral load to the structure and we obtain the force effect or the displacement in the event of an earthquake. If we suppose the structure to be in elastic region and we perform dynamic analysis, the type of analysis is dynamic, in which the equation of motion is used. We call it the response spectrum analysis, or if you talk about the AASHTO LRFD Seismic Design criteria code, they call it elastic dynamic analysis. So when you say elastic, it is the structure action, and when you say dynamic, it is the type of analysis. If you consider the structure to be of nonlinear behavior, you take into account the nonlinearity of steel and concrete, and if you perform a static analysis, it becomes a nonlinear static analysis, which is also known as pushover analysis. And if you take into account the nonlinear behavior or characteristic of steel and concrete and you perform a dynamic analysis, we call it a nonlinear time history analysis. So basically these are the four types of analysis that you can perform on any structure to obtain the effect of an earthquake. And today we are going to talk about the response spectrum analysis and pushover analysis. The response spectrum analysis will be used to obtain the demand in the event of an earthquake, and the pushover analysis will be used to obtain the capacity. I have done a simple comparison between the four methods that I have shown you here, and I have mentioned some of the advantages and the disadvantages of these four methods. If you talk about the static seismic analysis, the advantages are that it's relatively simple to understand and apply. You don't need rigorous calculations, and it's very effective and it's very quick. And the disadvantages are it doesn't take into account the dynamic response of the structure. As I said, in the event of an earthquake, the structure vibrates. There is an acceleration, or you can say force applied to the structure, and it must have some dynamic response to it, and this method fails to capture that. The non-linearity of the material is ignored because it's a static seismic analysis. We consider the structure to be in elastic region. We ignore the non-linearity, and it does not lead to detailed response in earthquake. So basically, as you know, in the event of an earthquake, there would be vibration. The structure might respond differently with time. The deformations may increase or decrease with time, and thus, since it's a static seismic analysis method, it doesn't give us the detailed response in the event of an earthquake. It might give us the maximum deformation and stuff like that, but it doesn't give us what will the response with respect to time. When you talk about elastic dynamic analysis or response spectrum analysis, there are certain advantages with this method, and I have listed down the advantages here. You can see that it applies the dynamic equation of motion for earthquake, and hence it can give us the vibration characteristic of the bridge during the event of an earthquake. Different modes of excitation are considered for obtaining the earthquake effect, so it is more realistic, and you can consider damping while obtaining results. So again, you take into account the practical aspects while performing this kind of analysis. While there are certain disadvantages with this method, you cannot consider the non-linearity of the material. It is ignored, and it does not lead to detailed response again. So basically, you do not apply a timed force to the structure, and it does not lead to detailed response in terms of in the event of an earthquake. And here we have different type of combination methods, and the result depend on them. So basically, you have to be very sure about the combination method that you are applying, and if you are not very much confident about the combination method you are applying, the results might not be as practical as you want them to be. Now, talking about the nonlinear static analysis or pushover analysis, there are certain advantages. It is simple to understand and apply. If you see the theory behind the pushover analysis, which I'm going to talk about later during the session, you will see that it's relatively very simple to apply, and we take into account the nonlinear behavior of concrete and steel. So it is more realistic, and it considers the second order effect. You can consider the second order effect like P delta effect in this kind of analysis, so it is more practical. But the disadvantages are that it doesn't take into account the dynamic equation of motion. The vibration modes are not considered. The structure is supposed to excite only in one direction or mode, so you do not take into account the different modes or different directions of excitation and the various methods of force distribution, and hence there is no specified scheme. When you talk about the pushover analysis, there are certain different type of approaches, the different load distribution when it comes to application of force, and hence there is no specified scheme by which you perform this type of analysis. So again, you have to be very experienced to choose the type of load distribution for performing this type of analysis. Now let us talk about the fourth category of seismic analysis, which is time history analysis. It is the best among the different type of analysis we talked about, and it has certain advantages. It considers the dynamic equation of motion, so it is realistic. It takes into account the nonlinear behavior of concrete and steel, so again it's more practical. It gives the displacement, velocity or acceleration of the structure with time. So basically it gives us the response of the structure with respect to time. So it is better, and it considers damping, so it's more realistic. But there are certain disadvantages with this method. It is very difficult to understand and apply. As you know, you have to apply the equation of motion, and you have to consider the nonlinear behavior of concrete and steel. So it is a little bit complicated to understand and apply, and it generally requires a computer software. If you want to perform this type of analysis with hand calculations, it might take months to perform even this type of analysis for a simple structure, and it requires additional parameters to perform this type of analysis. So basically, when you are performing time history analysis, you have to take into account so many parameters of the bridge that sometimes it becomes disadvantageous. Now let us talk about what the AASHTO LRFD code says about seismic analysis. So I have listed down several specific features of our code, and first of all, I'll be talking about the different highlights. So the code adopts a 7% in 75-year design event for the development of a design spectrum. and we should ensure sufficient conservatism. And there are several categories. They are A, B, C, and D, and there are different type of design. I discussed the details about these categories and design in the previous session, but just to recapitulate, I'm going to talk about the different categories of SDC here. In SDC-A, no displacement capacity check is needed as per the code. No capacity design is needed. SDC-A minimum requirements are to be there, and you don't have to perform liquefaction analysis. So basically, when you are moving from A to D, the code becomes more and more stringent. So here you will see that for A, you do not need to perform any displacement capacity check, but for B, you need to perform implicit displacement capacity check. Here, when you talk about SDC-C, it is again more stringent if you compare it with SDC-B, and the SDC-D is the most stringent amongst all. So basically for SDC-C, you need to perform pushover analysis, you need to perform capacity design. The SDC-D level of detailing is required, and the liquefaction assessment is must for this kind of category. And talking about the type of design, the type 1 would be a ductile substructure with an essentially elastic superstructure. The type 2 design would be an elastic substructure with a ductile superstructure, and the type 3 would be elastic superstructure and substructure with a fusing mechanism at the interface between the superstructure and the substructure. So basically, when you are talking about type 3 design, you have to have certain type of bearings which control the flow of forces from the superstructure to the substructure. Talking about the flow charts that are given in the code for performing the check for these kind of categories. Here you can see the check for SDC A, B, C, and D. So SDC A doesn't require the demand analysis, but SDC B, C, and D require the demand analysis. So for obtaining the demand, we are trying to simulate SDC D here. Before I actually start talking about the elastic dynamic analysis for a SDC D structure, I'm going to talk about the performance-based design. The performance-based design is an approach which focuses on the objective of a building asset in order to prescribe desired results instead of the way and the method to get the things done. So basically, when you talk about performance-based design, you first of all set up what is the performance criteria for a structure. So basically, you set up what is the demand, and based on the demand, what is the capacity of the structure. The assessment would be okay as per the performance-based design when the capacity is greater than the demand. So in the session earlier, I talked about the force-based design and the displacement-based design, and they are subcategories of this performance-based design. So basically, whatever we are doing right now, the different in this session, we are trying to talk about the performance-based design, and explicitly we are going to talk about the displacement-based design. So let us now talk about the demand analysis. So for obtaining the demand, there is a flow chart given in the AASHTO LRFD Seismic Design criteria code, and here you can see the different steps that you have to perform for obtaining the design check. So if you talk about the demand analysis, here you can see that for the seismic design category A, you do not need to perform this kind of analysis as I said earlier, but for B, C, or D, you use the procedure 1 or 2. So here you can see the procedure 2 is elastic dynamic analysis, procedure 1 is equivalent static analysis, and procedure 3 is nonlinear time history analysis. Today we are going to talk about the elastic dynamic analysis. There are certain considerations or guidelines which the code specifies for performing this type of analysis. Here you can see that first of all, we need to take into account different modes for performing this type of analysis. The damping must be selected as 5%, and the results in different modes should be combined as complete quadratic combination. So as I said earlier, there are different methods of combination of results for elastic dynamic analysis, and the complete quadratic combination is one of them. So the code specifies that we have to combine the results as per the complete quadratic combination. I'm going to talk about what this combination is, but before we do that, let us talk about the theory of response spectrum analysis. So as I said earlier, response spectrum analysis is a dynamic analysis which combines the response spectrum with time period of the structure. So basically this kind of analysis, it utilizes a equation of motion to obtain the effect of the structure in the event of an earthquake. So the mass matrix multiplied by the acceleration, the damping multiplied by the velocity, and the stiffness multiplied by the deformation will be equal to the mass of the structure multiplied by the ground acceleration. But the question is how to obtain the ground acceleration. So the ground acceleration would be obtained as a combination of response spectrum and the eigenvalue period. So basically when you are performing the response spectrum analysis, the step one will be to obtain the period of vibration in different modes for the structure, and on the basis of that period you will obtain what is the ground acceleration that you have to use to be used in this equation. So let me talk about the two requirements to obtain the acceleration. So I said that you need to have a response spectra. So what is this response spectra? The response spectra is a function of period. You can see that it's a function of period with the spectral acceleration, and in the last session I talked about how you can obtain this kind of response spectra as per the code. The code has different charts. You can obtain the different values that you need to obtain this kind of response spectra. After you obtain the response spectra, you will obtain the period of vibration of the structure in different modes. So here I have shown the example of two modes of vibration for this structure. It's a pedestrian bridge, and you can see the mode 1 of vibration and mode 2 of vibration. And so basically the time period of that vibration will be combined with the response spectra to obtain the acceleration. So I performed eigenvalue analysis and I obtained the different modes of vibration and I obtained the period. Once I obtain the period, I will plot the period with the response spectra and I'll obtain what is the acceleration for different modes. So here you can see that for the mode 1 the period is 2.41 seconds. Sorry, the period is 2.41. So we will obtain the acceleration as 0.75 times the acceleration due to gravity. So the 2.41 period will be somewhere here, and when you draw a straight line and you extend it towards the spectral acceleration, you will obtain an acceleration of 0.7 times multiplied by g. And for the mode 2, the period would be 1.04 seconds. So the acceleration would be approximately 1.25 times the acceleration due to gravity. So this is how the response spectrum analysis or the elastic dynamic analysis work. You will obtain the acceleration that you will multiply with the mass matrix to be used in the equation of motion to obtain the effect on the structure. As I said earlier, you need to combine the results from different modes while you are performing response spectrum analysis, and there are several approaches to do that. The first and the easiest approach is the absolute sum, where you just keep on adding the effect that you obtain from individual modes. The second amongst them is SRSS, which is the square root of sum of squares. So basically you take a square root of the sum of squares of different effects. So if you talk about the reaction at a particular bearing, you will obtain the reaction due to different modes, and then you will combine them using the square root function. But the complete quadratic equation, it's a little bit complicated, and this is what AASHTO LRFD specifies, and it takes into account the damping ratio as well as the response and the peak response, and this is how this is combined. So it's a bit complicated, but this is what the AASHTO specifies for obtaining the results of elastic dynamic analysis. So now we'll talk about how you can perform elastic dynamic analysis in Midas Civil. But before I continue with this, I would like to tell you people that if you have any questions, you can send your questions through the questions window, and I'll be taking all the questions towards the end of the session. But if you have any questions, if any question come across your mind while I'm doing the session, you can post the questions and I'll take up all the questions towards the end of the session. So the different steps that you will follow to perform the elastic dynamic analysis on Midas Civil are these 3 steps. So first of all, you will perform the response spectrum. You will define the response spectrum function. Then you will create a response spectrum load case, and then you will perform the analysis to obtain the response spectrum results. So now let me take you to Midas Civil itself and let me show you how you can perform the elastic dynamic analysis in Midas Civil. So now I'll be switching to Midas Civil itself, and then I'm going to talk about how to perform this kind of analysis in Midas Civil. So right now I'm at the work window of Midas Civil. I hope you guys can see the work window of Midas Civil on your screen. And today we are going to talk about the response spectrum analysis on a conventional bridge. Here, let me first talk about the specifications of this particular bridge. It's a skewed bridge and it's a steel composite bridge, and for performing different type of analysis on this particular bridge, I have considered the different elements of the bridge. You can see that the substructure is modeled, the piers and the pier cap are modeled. I have modeled the bearing connecting the pier cap and the pier, and I have also modeled the foundation so that I can perform the soil structure interaction. Basically for this particular bridge, I modeled 3 different stages. You can see stage 1 where the substructure has been erected, then stage 2 when the steel girders have been erected. You can see that at this stage the steel girders are not composite with the concrete deck on the top, and in the 3rd stage the concrete becomes composite with the steel girder and it becomes a composite bridge. So these are the 3 different stages that I have modeled in this particular bridge. So for performing the elastic dynamic analysis, first of all we need to define the mass of the structure. For defining the mass, we have 2 options in Midas Civil. The first option is you can define the mass manually. So for defining the mass manually, you can go to load and then you can define the mass manually. So here you can see that when you go to load and static loads, you can define the nodal masses. You can define different type of nodal masses. You can select the nodes and you can define the nodal masses. If you have defined certain static loads on the bridge which you want to be converted as masses while performing seismic analysis, you can use the function load to masses. So let's say you have the barriers. The barriers are not considered as I haven't modeled the barrier in this particular bridge. I just applied the barrier load as a uniform load to this particular bridge. So what I'll do is I will convert the barrier load into mass by using the load to mass function. And once I do that, you will see that the barrier load has been applied as the mass onto the edges of the bridge. Secondly, if you want to use the wearing course and you want to convert the wearing course load into the mass, then you can also do that. So I selected the load case as wearing course, and once I click on OK, you will see that the wearing course has been converted into the mass. The second method of defining the mass to the structure is converting the self-weight into the mass. For converting the self-weight into the mass, you will go to the structure option and you will click on structure type, and here you can see that we have an option called convert self-weight into masses, wherein you can convert the self-weight into mass in X, Y, and Z direction. Once you do this, the self-weight will automatically get converted into the mass in the X, Y, and the Z direction. Now, as I said before, for performing the elastic dynamic analysis, you need to obtain the period of different modes of vibration. So for obtaining the period, we will perform an eigenvalue analysis. So I'll go to analysis and I'll go to eigenvalue analysis, and here I'll define the number of modes that I want for this particular bridge. So I've defined the number of modes to be 50, and once I do this, I have defined the eigenvalue analysis for this particular bridge. After we do this, we can define the specifications for response spectrum analysis. For that, I'm going to go to load. Here, when you go to load, you will go to the seismic section, and here you can see that in the seismic section you can define the response spectrum function. First of all, I'll click on Add, and here you can see that you can specify the period and the spectral data. In Midas Civil, we have a built-in function for the definition of response spectra as per AASHTO LRFD 6th edition, and you can select the site class. You can define the peak ground acceleration, the spectral acceleration coefficient at short period and long period, and you can specify what is the response modification factor. And once you click on OK, the response spectrum will be automatically defined by the program. So basically all you gotta do is specify the features, and here the response spectrum will be automatically defined. Now once I click on OK, you will see that the response spectrum function has been defined. So this is step one. Right now you have defined the response spectrum function, but now you will tell the program that you will use the response spectrum function to perform the response spectrum analysis in the X and the Y direction. So for that, I'm going to go to the response spectrum load cases, and I'm going to create a response spectrum in X direction. So I'll name it as RSX, and I'm going to click on the response spectrum function that I'm going to use for it, and I will click on apply damping method. I will apply the damping ratio for all modes to be 0.05, and once I click on OK, and I click on Add, and here the response spectrum load has been applied. So basically I have specified the response spectrum load in the global X direction. For applying the response spectrum load in the global Y direction, I can put the excitation angle to be 90 here, and again I click on Add to obtain the load case RSY in the Y direction. In Midas Civil, you can click on the modal combination control here, and here you can select what type of modal combination do you want. So basically, as I said before, AASHTO LRFD specifies that we use the complete quadratic equation. So we will select CQC here, and if you want to specify factor to any specific mode shape, you can specify the factor here, and once you click on OK, you are using the CQC method for performing the response spectrum analysis. So as of now, the definition for response spectrum analysis is complete, and now we are going to perform analysis to obtain the results for response spectrum analysis. I'm not going to perform the analysis in front of you because it might take about 30 seconds. So I'm going to open a model in which I have performed response spectrum analysis, and I will use that model to show you the results of response spectrum analysis. So after I perform the analysis, I can go to the results tab, and if I want to obtain the deformation due to response spectrum analysis, I can go to deformation, and I'll go to displacement contour, and I will obtain the deformation for the response spectrum in the X direction. So I will select the load case as response spectrum in the X direction. I will select the component as DX, and I will click on legend, and this is how the deformation in the X direction looks like. If you remember in the last session, I told you that AASHTO LRFD specifies that the foundation must be taken into account to perform the demand analysis. So in this particular model, we do have the foundation with us. So basically, you are performing the response spectrum analysis and solid structure interaction in the same model file. You can obtain the demand from this function. If you want to obtain the forces, you can go to Result, Forces, Beam Diagrams, and let us see what is the bending moment generated in this particular bridge for the pier section after we perform the response spectrum analysis. So this is how the bending moment is generated. You can see the bending moment, the highest bending moment is being generated in the pier section here. So basically you can obtain the force results. If you want to obtain the stresses, you can go to the stresses section and you can obtain the stresses due to the response spectrum loads. So this is how you perform response spectrum analysis in Midas Civil, and you obtain the results for the same, and basically the demand analysis section is completed. Now I'm going to go back to the presentation again, and we are going to talk about how to obtain the capacity from Midas Civil. So the step 2 would be capacity determination, and here we are going to use the pushover analysis as specified in the code for STC-D. For STC-B, C, and D, the bridge bend shall specify the following specification. The demand must be less than the capacity, and for the calculation of the capacity for STC-D, we can perform nonlinear static analysis, that is pushover analysis. But for STC-B and C, you can use the equations which are provided in the code, and you can obtain the capacity. For performing the nonlinear static analysis, there is a procedure given in the code, and basically this procedure has to be followed, this criteria has to be followed while performing the pushover analysis. But before we actually do the pushover analysis on Midas Civil, I would like to talk about the theory of pushover analysis and what exactly this type of analysis is. So as I said earlier, pushover analysis is nothing but static nonlinear analysis. So the load application will be static, and we will consider the nonlinear behavior of concrete and steel present inside the bridge. So it's a technique by which a structure is subjected to an incremental lateral load of certain shape. So as I said, there are different type of load application mechanism when you talk about pushover analysis. The sequence of cracks yielding plastic hinge formation and failure of various structural components are noted. So as you keep on increasing the lateral load, some of the elements of the bridge will yield, plastic hinge formation will take place, and there would be failure of various structural components, they would be noted, and the structural deficiencies are observed and rectified. So once you are performing pushover analysis, you will visualize, okay, this is the part of the structure which is going to be affected the most. This part will have a plastic hinge generation, or this part is prone to failure. So you will do the retrofitting, etc. What is required for that particular structure. And here I have shown you the incremental loading that you will apply for performing the pushover analysis. So you will keep on increasing the lateral load. Here I have used the method of uniform acceleration. So basically all the masses inside the structure, a uniform load will be applied in different increments. Talking about the nonlinear material behavior, as you know that the structural material has a nonlinear behavior after a specific loading. So this behavior will be taken into account while you are performing the nonlinear analysis. And when you talk about the concrete, this is how the concrete behaves. And when you talk about steel, this is how the steel behaves. So basically for pushover analysis, you are combining the increments in the load with the nonlinear behavior of concrete and steel to obtain the effect on the structure. And this is how it is done. So you can see when you increase the base shear, the structure goes from linear to nonlinear behavior, and you obtain the capacity spectrum for the structure. Then you combine the demand spectrum with the capacity spectrum, and then you obtain the performance point of the structure. Now let us talk about how to perform pushover analysis in Midas Civil. So basically there are 5 steps involved in performing pushover analysis in Midas Civil. First of all, we need to define the pushover global control. Then we need to define the load cases for the pushover analysis. Then we define the hinge properties. Then we assign the hinge properties, and we perform the analysis to obtain the results for pushover analysis. So the step 1 will be the definition of pushover global control. So you will go to design. This is the path that you will follow for performing the pushover analysis, and this is how the global control looks like. If you want several static loads to be considered as an initial load for performing pushover analysis, you can do that in global control. Then you will define the load, the different loading mechanisms, how the loading increment will take place. You can either choose a force-based approach, which is the load control, or you can use the displacement-based approach, which is used for obtaining a desired displacement. You can select the different type of load patterns such as mode shape, modal, and uniform acceleration. Then you can define the pushover hinge properties. For defining the pushover hinge properties, we have different options in Midas Civil. I'm going to talk about the different options while I'm going to show you how to actually perform pushover analysis in Midas Civil. And once you are done with these definitions, you perform the analysis to obtain the capacity curve as per the pushover analysis. So now let me take you to Midas Civil itself and let me show you how you can perform pushover analysis in Midas Civil. So again, we are back to the model in which we perform the response spectrum analysis or the demand analysis, and now I'm going to show you how to perform the pushover analysis in Midas Civil. For performing the pushover analysis, you will go to the pushover menu bar in Midas Civil, and the first thing is to define the global control. So you will click on global control and you have different options here. So as I said before, in global control you can define whether you want to take into account several loading or any initial loading before the earthquake load is actually applied onto the structure. So you can either import the static analysis results for self-weight or construction stages or barrier or wearing codes or whatnot, or if you want to perform a nonlinear static analysis for the initial load too, you can click on perform nonlinear static analysis for initial load. But I'm pretty confident that the structure will not go into the nonlinear region for initial loading, so I'm gonna keep the self-weight and the wearing codes and the barrier load as an initial loading before the earthquake lateral load is applied. It has several other options, such as you can control the nonlinear analysis option, what are the different number of iterations that the program is supposed to perform. Then if the program encounters a yield in the shear component, and if you want the program to stop the analysis at that spot, you can check it on. Similarly, if there is an axial component collapse, you can check this option on and the analysis will stop. So this is how you can control globally what is going to happen in the pushover analysis. While performing the pushover analysis, the code specifies that we need to take into account the nonlinear behavior of the soil, and you can do that in Midas Civil. So basically, when you are defining the point spring supports that I have defined here, you can take into account the nonlinear behavior of the soil to perform pushover analysis. So as you can see here, I have defined the stiffness of the spring like this, and you can see that I have defined a nonlinear spring for performing the pushover analysis. These springs can be automatically defined in Midas Civil. All you gotta do is you can go to boundary and you can go to integral brace support. You can go to pile spring and you can specify the properties of the soil, and Midas Civil will automatically generate the soil springs as per Matlock and Resi method. So basically all you gotta do is specify what type of soil it is, what is the ground level, the diameter of the pile, and the coefficient of subgrade reaction. Once you do these definitions, Midas Civil will automatically generate the lateral springs for you. Okay, so once we are done with the definition of global control, we can define the load case for pushover analysis. For defining the load case, I'm going to go to pushover load cases. I'll click on that and I'll perform the pushover analysis in the X direction. So I'm going to name it as push X. If I want to consider P delta effect in pushover analysis, I can check this option on, consider P delta effect, and then the program will consider the P delta effect while performing the pushover analysis. And you can use the initial load while you are obtaining the results from pushover analysis, and here you can use the increment method to be either load control or displacement control. I want to perform a pushover analysis to obtain a maximum translational displacement of 7 inches in the X direction, so I specified the global maximum translational displacement to be 7 inches. But if you want to select any particular node and define the control with respect to it, you can do that. Now the different load patterns that are available in Midas Civil are listed here. You can either use the static load to be applied as a lateral load, or you can apply a uniform acceleration in the X, Y, or Z direction. You can also ask the program to apply the load as per the mode shape, or you can use the normalized mode shape multiplied by mass option to obtain the load. Here we are going to use the uniform acceleration approach in the x direction. So I'm going to specify the direction as dx and the scale factor as 1. And similarly, I'm going to perform a pushover analysis in the y direction, and I'm going to consider the p delta effect. And again, the global maximum translational displacement is assumed to be 7 inches, and I'm going to select the uniform acceleration load pattern, and the direction would be dy this time. And once I click on add, you can see that the pushover load cases have been defined in the x and the y direction. Now I'm going to define the hinges. As you know, the pushover analysis takes into account the nonlinear behavior of several elements in the bridge. We simulate that with the help of a hinge. So I'll click on add, and here I'll create a hinge. So first I'm going to create a hinge for the pier, and it is a column type of element, so I'm going to select column. Here you can select what type of material is there. Is it a reinforced concrete or a steel or SRC felt type of cross section? So it's a reinforced concrete pier, so I'm going to select the material type as reinforced concrete. Now you can define the hinge, and in 3 different type of definitions. You can either use the moment rotation. So basically when you select the moment rotation, you specify what is the moment and rotation. So basically the moment curvature curve that you obtain after performing the detailed analysis on a cross section can be provided here, or you can use the moment curvature M phi lumped or distributed option. Since this is a compression member, we are going to use the PMM interaction in status determination. So I click on FX, and when I click on the yield surface properties, you will see that the PM interaction curve will be used to obtain the plastic hinge or to obtain the nonlinear characteristic of the element. So basically the program will automatically calculate the PM interaction curve so that the hinge can be determined basis on that. But if you want to specify your own properties, you can click on the user option, and then you can create your own PM interaction curve to be used. Okay, so once I click on OK, the pier hinge has been defined, and I want to define the hinge for the pile too. So I'm going to define the hinge for the pile. Again, the pile is a compression member, so I'm going to select the PM interaction in status determination. So this is how I have defined the hinges for the pier and the pile. Now I'm going to assign the hinges to the pier and the pile. So I'm going to select the member of the pier. So here I'm selecting all the members of the pier. So what I'm going to do is I'm going to double click on the pier cross section here, and you can see that the pier elements have been selected. They have been highlighted in red. And now I can drag and drop the pushover hinge for the pier onto them, and this is how the hinges have been defined. So it's pretty easy. Just double click on the cross section, the elements will be selected, and you can drag and drop the hinge that you have defined onto the elements. So this is how the hinge definition has been done. Now when you talk about the hinge creation, you need to define the reinforcement in the cross section. The reinforcement must be defined in the design tab in the ribbon menu, and whatever code you select here, this code will be used to obtain the PM interaction curve or to obtain the properties, the parameters in the PM interaction curve. So here I'm going to go to the column section data for checking, and I'm going to define the reinforcement for the pier and the pile. So this is how the reinforcement has been defined for the pier and the pile element. And once you do this, once you define these reinforcement, you can perform the analysis and you can obtain the results for pushover analysis. So now I'm going to open a model in which I have already done the pushover analysis, and I'm going to show you how the results for pushover analysis would look like. So first of all, when you perform the analysis, you can see the definition of different yield surfaces that the program has automatically generated for the reinforced concrete pier and the piles. So when I click on assign hinge properties and I right click to obtain the properties, I can go to yield surface properties, and here I can obtain the PM interaction curve. So once I obtain the yield surface properties, I can click on show value and it gives me the PM interaction curve right here. Again, if I want to specify the user defined parameters, I can go to the input method as user. So this is how the properties have been calculated by the program. Now if I want to obtain the results for pushover analysis, I can go to the pushover menu and I can obtain the reactions, deformation, forces, etc. So let us see the deformed shape due to pushover analysis in the X direction. So here I'm going to check on the deform option, and once I click on apply, you will see this is how the deformation has taken place. Let me check on the lesion so that we can obtain the results. I can move to different steps and I can obtain the deformation. I think the screen transfer is taking some time, so I'm going to wait for some time till you guys see what's actually happening. So here you can see how the pushover steps are being increased and how the deformation increases with the steps. Now let us see how the hinges are being created in this particular model. So you can see the hinge status. So I'm going to go to status of yielding and I'm going to go to RY. I'm going to hit apply, and the blue represents that the hinges are not formed. So I keep on increasing the steps. Again, the hinges are not being formed. Now in this region you see that the hinges have started to form. So you can see at the bottom of the pier the first hinge has occurred, and this is how it is shown. The color code tells you that the hinge has been formed, and when I go to the last step you will see that other hinges have been formed. So basically you can obtain the hinges, the status of yielding of the hinges from pushover analysis, and you can scroll down to different steps to perform pushover analysis to obtain the status of yielding. For this particular example, I performed the pushover analysis to have a maximum translational displacement of 7 inches, so the hinges are only occurring at the bottom. But if you do this kind of analysis for about a foot deformation in the event of an earthquake, then you will see hinges occurring at multiple locations on the pier. You can obtain the pushover curve by clicking on the pushover curve here, and in the X direction this is how it appears. You can see that after approximately 6 inches of deformation, the structure turns into nonlinear, and similarly in the Y direction the behavior of the structure is almost elastic till 7 inches of deformation. Now let me go to the pushover result table and let me show you the different result tables that you can obtain for pushover analysis. So here, if you want to obtain the yield step table, you can go to the yield step and you can obtain the yield step for pushover Y and X in the Y direction. And once I click on OK, you can see the status of different elements while performing the pushover analysis, and when is the first and the second yield occurring. And you will see that for the elements, for the pier elements, you will have the yielding step as step number 38 and 39 respectively. So this is how pushover analysis is performed in Midas Civil. We do have specific tutorials will tell you how to perform this kind of analysis and how to obtain the results from the same. So this is what I wanted to convey to you guys today. If you guys have any questions, please let me know through the questions window and I'll be more than happy to answer any of your questions. Okay, so I've got a question here. The question is, does Midas Civil automatically calculate the moment curvature too while performing the pushover analysis? Yes, Midas Civil automatically generate the moment curvature curve as per the defined code, and it will perform the pushover analysis based on those specifications. Okay, I've got a question here, and the question is, how can you put the pushover curve with the response spectrum curve together while they have different axis parameters? We cannot do that, but what we can do is we can change the pushover capacity curve, the parameters of the pushover capacity curve, and then we can put them with the response spectrum curve. So basically here you can see that now I changed the pushover capacity curve and I changed it to spectral acceleration versus spectral displacement, and now I can put the response spectrum here. So basically you need to convert the capacity curve that you obtain from pushover analysis to the required axis, and then you can put the response spectrum along with the capacity curve. So basically the capacity curve, this one shows resultant base shear versus monitor displacement, then shear coefficient versus displacement, shear coefficient versus drift, load factor versus displacement, and then when I click on for performance point, it gives you spectral acceleration versus spectral displacement. Okay, for those who want the recording of this session, we are going to upload the recording on YouTube and we are going to send you the link. So after this session is complete, we are going to send you the recording. If you guys have any more questions, please let me know the question through the questions window and I'll be happy to answer your questions in real time. Also, you can send your questions to us through email, and I have put our email address on your screen now. It is ts@midasuser.com. If you have any question, you can send your detailed question on this particular email address, and our engineers will be assisting you with your questions. So thanks a lot for being with me today, and I hope the session was fine. And now I would like to ask Daryl to continue, and he's going to give you more information about the upcoming sessions.
Okay, thank you, Nithil, for your presentation. So before I just close up the seminar, I just want to show you just a couple of things. So as Nithil said, we do post up our recordings up on YouTube. So for example, if there are any past recordings or past webinars that you'd like to see, you can just go to our website, goodengineers.com, to view the recording. We'll be posting this recording shortly, and we'll let you know as soon as it's posted so that you can review it on your own time. And also, I just wanted to remind you of the upcoming seminars that we have. So this month, on the 10th, we'll have a seminar on curved steel eye girder bridge design, the in-depth case study and discussion. And then on the following week, on the 17th, we'll have the numerical modeling and analysis training for curved steel eye girder bridge design. So just make sure to mark those dates down in your calendar if you're interested in attending. And once again, you can visit our website to register for the seminars. Okay, so that will do it for today. Thank you again for taking the time to attend the seminar. We hope that you found it useful, and we hope that you'll have a good day. Take care now.